Hi everyone, welcome back. This is lecture 19, and we're starting to wrap up our study of pairs of random variables. So to recall the last lecture, we learned about functions of random variables and expected values of those functions. And specifically, we were interested in the variance of the sum of x plus y. And we showed that this is equal to the variance of x plus the variance of y plus this cross term, which was the covariance, 2 times the covariance. So this covariance is an expected value, and specifically, it's the expected value of x minus mu x times y minus mu y. And of course, this product is a random variable, and it's instructive to think about what sort of random variable this is. So when covariance x and y is greater than 0, it says that the expected value of this random variable is positive, and it says that more often than not, x minus mu x times y minus mu y is greater than 0. But the way this occurs is that this corresponds to saying x minus mu x and y minus mu y tend to have the same sign, because the product is positive if the two terms are either both positive or both negative. On the other hand, if covariance xy is less than 0, then x minus mu x, y minus mu y tends to be less than 0. And that corresponds to x and y minus mu y tend to have opposite sign. So in essence, the way to think about this is that positive covariance says that when x goes up, i.e. when x is bigger than its mean, y tends to go up. Y tends to be bigger than its mean. And negative covariance says that when x is bigger than its mean, y tends to be less than its mean. So as x goes up, y goes down. So in the case of positive covariance, they tend to move together in the same direction. With negative covariance, they tend to move in the opposite direction. And then I just want to make a point here that you can't forget that this product, x minus mu x, is a random variable. And when I say, oh, this product is greater than 0, I don't mean it's always true. I just mean that for many sample pairs that you observe x and y, it tends to be true. And similarly, when I say that the product tends to be, it's less than 0, I mean it tends to be. That is that it's happens sufficiently often such that its expected value is negative. Next, recall that to understand covariance, whether it's high or low, it's useful to normalize the covariance by the square root of the variance of x times the variance of y. And this product is called the correlation coefficient. And we learned in the previous class that rho is always between -1 and 1. And that when rho is 1 or -1, the natural situation in which that arrives is when y is equal to ax plus b, particularly a greater than 0 implies rho equals 1, and a less than 0 implies rho equals -1. So how close rho is to 1 or minus 1 gives you a sense of how close sample value pairs x and y are to the line, to some line y equals ax plus b. So we saw this last class by looking at plots of sample pairs of x and y, and we considered three particular cases. In the middle was the case of rho equal to 0, and in this case, it looks like the x's and y's are independent. Like they're simply scattered about. Learning that maybe x is positive doesn't seem to give you any clue about whether y is positive or negative. On the other hand, when rho was zero point 0.9, we saw that the x's and y's were kind of lying along the line y equals zero point 0.9x. And there's some noise in those observations. Why? But you definitely can see the pattern of the x's and y's lying along a line. And similarly with negative zero point 0.9 correlation, you see the exact same thing, but with the sign of the y's reversed. So when we looked at these figures last class, I just told you that each xy pair is such that e of x is equal to e of y equals 0, variance of x equals variance of y equals 1. And then for each figure, there I managed to construct the xy pair to have a certain value of rho. In fact, I used a very specific distribution on the xy pairs to do this. It's perhaps the most important distribution on xy pairs that are correlated. So those xy pairs in the last figure were generated using a bivariate Gaussian PDF. And this is a pretty complicated PDF. It has 5 parameters. It has mu x, the expected value of x, mu y, the expected value of y, the standard deviation of x, and the standard deviation of y. And it includes the parameter rho, which in fact is the correlation coefficient of x and y. And these things are all put together in the following PDF. The numerator is an exponential function, and the argument of the exponent, everything here in the square brackets, is a big quadratic term. It includes things that look like x squared and y squared, normalized by mu x and sigma x, mu y and sigma y. And then there's a cross term here, uh, which is also kind of complicated. And the cross term involves the correlation coefficient rho. So to understand this, to get a sort of a first sense of how this works, let's look at the case where rho xy is equal to 0. In this case, the joint PDF of x and y, the big exponent, it becomes this, x minus mu x over sigma x squared plus y minus mu y over sigma y, that's squared. And down in the denominator, you just simply have 2 times 1 minus 0. And this whole thing is over 2 pi sigma x sigma y square root of 1 minus 0 squared. And we can simplify this and write it's 1 over 2 pi sigma x sigma y. And now the exponent can be written as minus 1 half x minus mu x over sigma x squared minus 1 half y minus mu y over sigma y quantity squared. And then we can break this apart in the following way. this equals 1 over square root 2 pi times sigma x e to the minus x minus mu x squared over 2 sigma x squared times 1 over square root 2 pi sigma y e to the minus y minus mu y squared over 2 sigma y squared. And what we see here is that this is equal to a Gaussian PDF for x times a Gaussian PDF for y. And so what we see that this formula in the case of rho equals 0 is that x and y are Gaussian mu x and mu y sigma y random variables and independent. For rho not equal to 0, the instructive way to think about this is to look at the case where the PDF is a constant. This occurs when the term in the square brackets is a constant, and the term in the square brackets equals some constant, say we call it c prime. This is the equation of an ellipse in x and y. So typically you have something like this. That you'll have some kind of an egg-shaped level set where along this set the PDF is a constant, and typically it's kind of like a mountain. The smaller and smaller circles are higher up. So my drawing is kind of terrible, and it's better maybe just to look at this via a MATLAB plot. So here we have 3 versions of this Gaussian PDF. In all 3 cases, we have mu x is equal to mu y is 0, standard deviation sigma x equals sigma y equals 1, and we have the same 3 values of rho that we've looked at before. Specifically, rho is minus 0.9, rho is 0, and rho equals 0.9. And we see 2 different sort of representations of this PDF. First, we see the same figures we saw before, where we generated 200 sample pairs of x and y for each version of the PDF, and here we see the negatively correlated pairs. Here we see the positively correlated pairs. And in the middle, we see XY pairs with no correlation at all. And then corresponding to these clusters of XY pairs, above it, we have the joint PDF that generated those pairs. So, so for instance, the pairs that for positive correlation were generated by the PDF on the right. And what you can see is that the points along here generated along the line y equals 0.9x, in fact, correspond to a ridge of probability along the line, along the same line, and that this probability kind of piled up in a ridge is what gives you XY pairs that lie along the line. And conversely, in the case of rho equals 0, we see kind of that the probability is along. In fact, it's the density is constant along any circle, and that the XY pairs are kind of all over the map, but concentrated towards the origin. And you see that here, and that the probability is kind of a circular mountain, Although my drawing looks like an oval, it's not supposed to. It should really look like a circle tilted in the plane. And then finally on the left with rho equals minus zero point 0.9, all the probability is along this ridge. And once again, the sample points are kind of in this concentrated along that line that runs right down the middle of the ridge. So this complicated bivariate Gaussian PDF has a lot of special cases and a lot of facts associated with them. The first one is that if you were able to do the calculation, and you can, and it's outlined in the book how to do it, you can show that out of the joint PDF, no matter what row is, you can find that X always has the marginal PDF, which is Gaussian with parameters mu x and sigma x, and Y has the marginal Gaussian PDF with parameters mu y and sigma y. So individually, x and y are simply Gaussian random variables, but they're Gaussian random variables that have a dependency through the parameter rho. If you're interested in showing how you derive this marginal PDF, you start with the fundamental formula. You integrate the joint density over all y to find the marginal PDF of x. And to do that, you have to rewrite this joint PDF as the marginal times another expression, which involves doing a complete the square exercise in the exponent. It's kind of complicated, but ultimately, by doing that, you have a term here that integrates to 1 because it's a another Gaussian PDF. The next fact is that it's a property of this complicated distribution that the correlation coefficient of x and y is indeed equal to rho, that the rho in this expression here, here, and here is in fact equal to the correlation coefficient of x and y. Showing it is in the book, and but it is kind of complicated. In lecture 18, we showed that if x and y are independent, that implies the correlation coefficient equals 0. In general, however, the reverse implication isn't true. You can have random variables x and y which have 0 correlation. The correlation coefficient is 0, but they are not necessarily independent. The Gaussian bivariate Gaussian distribution, however, is a special case when x and y are bivariate Gaussian and rho xy equals 0, then x and y are independent. In fact, we showed this when we introduced the bivariate Gaussian PDF. We did the special case just a few slides ago where we said rho is 0, and we watched this term fall out, and this disappeared, and this disappeared. And we saw that what was left was the product of Gaussian PDFs. This next theorem is one of the reasons why jointly Gaussian x and y are so important. And the theorem says that if we take a linear combination of x and y, for instance, a 1x plus b 1y, and then we take another linear combination, a 2x b 2y, then in fact, W1 and W2 are bivariate Gaussian random variables. Somehow linear processing of a pair of bivariate Gaussian random variables results in a new pair of bivariate Gaussian random variables. Um, what makes this theorem so useful is that the calculation of exactly what the joint PDF of W1 and W2 is then becomes really simple because all you have to do is sort of go back to simple principles and calculate the expected value of W1 and W2. Here it is generalized for WI, where I is 1 or 2. You calculate what the variance of each W is, and then by multiplying them together and taking the expected value, you can also get a nice simple expression. It looks a little complicated here, but it's simple for MATLAB, right? To get an expression for the covariance of W1 and W2. So the point is that uh, once you do these three calculations, you can write down a joint PDF, the bivariate joint PDF for W1 and W2 without doing any additional work. Generally, for most other uh, correlated pairs of random variables, deriving a PDF for two new random variables generated in this way is kind of a nightmare calculation. Here, in fact, it's surprisingly simple. Before moving on, it's worth emphasizing that really this is kind of two theorems in one. The first theorem we get is that if you take x and y bivariate Gaussian and you form some linear combination, that linear combination is Gaussian. It's not an obvious fact, and the fact that it's true is both amazing and super useful. And then we have, of course, W2 being some other combination is Gaussian. And then the most powerful fact of all is the theorem we have here that in fact together they are bivariate Gaussian. So going back to the example of the noisy observation, we have an output y, which is the sum of a Gaussian signal x plus a Gaussian noise z. And the signal x and the noise z are independent. So the thing to keep in mind is that x and z Gaussian and independent is a special case that implies x and z are bivariate Gaussian. And then it follows from theorem 5.21, the theorem we just saw, that that y equal to x plus z is also Gaussian. So then, because of that, we can find the PDF of y by just simply finding mu y, which is e of x plus z, which is e of x plus e of z, which in this example happens to be 0 if you look up the original example 514, and variance of y, which is variance of x plus c, which is equal to variance of x plus variance of z, because the covariance term is 0. So now we can just simply write down the Gaussian PDF of y. It's 1 over square root of 2 pi sigma y squared, but that's sigma x squared plus sigma z squared, e to the minus y squared. There would be a mu minus mu y squared, but that's equal to 0 times 2 sigma x squared plus sigma z squared. And that's our answer. And here is the same answer, just with nice typesetting. So this quiz is slightly more complicated than the previous example of the noisy observation. In the noisy observation, there were two Gaussians, but they were independent. In this case, we have x and y, and they're jointly Gaussian, and they're both mean 0 and variance 1. but in fact they have some correlation coefficient which is non-zero. So we see that in fact we're given all five terms. We know that mu x equals 0, sigma x equals 1, mu y equals 0, sigma y equals 1, and rho is equal to 1/2. So what this quiz is really testing is whether you can memorize the bivariate Gaussian PDF. So I'll try to memorize it here. So it's the exponent of minus, and I get x minus mu x over sigma x squared minus 2 rho xy x minus mu x over sigma x y minus mu y over sigma y plus y minus mu y over sigma y, the whole thing squared. And then this goes over 2 times the square root of 1 minus rho xy squared. And here, I'll admit, in fact, I cheated because I went back and looked at the formula just to make sure I was doing it right. And it reminded me that, in fact, that this square root shouldn't be here. So continuing, this is all over 2 pi sigma x sigma y square root of 1 minus rho xy squared. So now rho squared, since rho is a half, is equal to a quarter. And we can rewrite this as minus, we get x squared minus 2 times 1/2 x times y plus y squared all over 2 times 1 minus 1/4 all over 2 pi times 1 times 1 times 1 minus 1/4. And so this simplifies to 1 over the square root of 3/4 times 2 pi times e to the minus. And keep in mind that this minus sign is in front of the entire fraction. So we get e to the minus x squared minus xy plus y squared. And here in the denominator of the exponent, I get 2 times 3/4, which is equal to 3/2. And now we're just about done. Maybe I'll rewrite this one more time. So this is 1 over the square root of 3 pi squared e to the minus 2 x squared minus xy plus y squared over 3. And that's our bivariate Gaussian PDF of x and y with correlation coefficient 1/2. So here's the solution. And in fact, we got the answer right, but the solution, of course, skipped all of the algebraic steps. So chapter 5 has one more section that follows this. It's section 5.10, and it takes everything we've learned for two random variables, x, y, and generalizes it to n random variables, x1 through xn.